The final method that we're going to introduce for today is called genetic algorithm. So as the name suggests, you can see that it's actually based on biology, and in particular, the theory of evolution. So solution, you can see that we actually have in our optimization problem is being treated as if they are individuals. And then we basically try to artificially create the force of evolution in the hope that all the solutions they will recombine with each other and follows principle that's very similar to the natural reproduction, and eventually you evolve into a population that's more competitive in aggregate. Right, so this particular process is what we call the genetic algorithm, and in particular, I think the technique that we use the most is a concept that also directly borrowed from evolution. It's called natural selection. Right, so you want to use the evaluation of the solution, the goodness of the solutions, as a force to force the evolution to happen. So if you want to use any GA related function, all of them. All these functions that we mentioned in the subsequent slides, they are available from the Python lab. All you need to do is just use the this particular method. Just insert this particular statement at the beginning, and if this particular statement is executed correctly, it means that your Python lab is installed appropriately. If you receive any errors, please refer to the website of the textbook that we mentioned upfront. In week 1, you will see the installation instruction about how you can actually set up the Python lab. So later we will see a little bit of demos about how the method that we introduce over here get executed. So reference, of course, is the textbook chapter 12. You can actually see all the more detailed hands-on sessions. Today we're only going to very briefly go over some selected samples, but you should really do your own. Okay, so the concept over here is to treat the solutions as if they are all of them are being contained within this petri dish, right? So you see that all the solutions are inside, right? So every tool in our problem over here is basically one object on this particular dish, and we hope to initiate the evolution process inside this particular dish, right? So the way that it works is that we will try to evaluate the goodness of all the tools in the dish, and for the ones that's not performing as well when compared to the other current tools in the population, we are going to delete them, and we're going to replace them with the copy of the better ones. But of course, if you just simply replace all these like worst performing tools with the identical copies of some better ones, that doesn't really make a lot of sense. After all, what we want is a particular process that can gradually evolve new solutions that performs better. So the way that we copy the existing solution as a result should be designed to make the existing tool slightly different, and then you replicate that in the new dish, right? So all this solution that we use to replicate, to replace the deleted solution should be something that's similar to the existing best performing objects, but differs slightly. Okay, so not exactly the same, but they should be similar. Right, so this is what we call evolution. So the first biological mechanism that we will adopt is called mutation, right? So concept of mutation is actually very simple to imagine, right? So right hand side over here, this is one example. You have a DNA sequence. If you mutate a single element over here, single base over here, basically means that, for example, like one of the code inside the DNA, maybe due to some external forces, pollution, radiation, chemicals, so on and so forth, is being changed, right? For example, the code A is being changed to C. So the rest of the genome looks pretty much the same, but except this particular spot. And of course, because of that, the biological outcome potentially may be different, right? For the case of TSP, the mutation that happens at a particular point is represented by a swap, right? So for example, this is one example. the rest of the tools stay exactly the same, but you swap the sequence of 11 and 7, essentially just exchanging their current position, right? But I mean, in reality, you can actually apply this mutation anywhere throughout the tool. Okay, so this is one example about what will happen if you swap the sequence, right? So for example, if you follow the sequence is HC and then FIJE, right? So H, try to find H is over here, HC, and then FIJ, and then E, right? If you swap the sequence of F and I, what you get will be HC, I, F, J, E, and then B. Okay, so you can see that this particular action of swapping essentially is the same as the 2-up operation, right? When you swap a pair of the index over here, essentially you are deleting 2 existing H and replace it with the alternative, right? So this is essentially a 2-up operation. But the major difference over here is that unlike the local search algorithm, where all the potential 2-up swap will be evaluated in each and every iteration, in this particular step, mutation step, they are randomly generated. Means that for each and every solution, you only generate couple of swaps, right? But not comprehensively. Okay, so you delete the worst performing solution from the population, and you replace those vacancies with these potential swaps. So if you do it in the TSP lab, this is the lab we talk about, like the tools. If you print out their sequence, they are just a sequence of the node ID that we visit according to this particular order over here, right? So if you specify that you want to mutate the index number 3, for example, this is 0, 1, 2, 3, it means that the order of 3 and 4 will be exchanged, right? So instead of 1 and 12, you get 12 and 1. And of course, the purpose is to search, right? So what we will do is that inside the algorithm, we will maintain a virtual dish, right? So this virtual dish over here pretty much play the role of the physical petri dish in our biological lab, right? So then all the germs, for example, originally contained on the dish, they are essentially the tool objects that we have in our TSP. So the first method will iterate over all the tools and delete the tools that's not performing so well. And the second method will be the mutation, right? You replace the deleted tool with mutated current copies of the survivors. All right, so this is how it goes, right? So if you do this, you can initiate a population. This is the function in which you will randomly generate a lot of tools, and you'll put it inside a variable called P. This is the dish that we use to hold the current population. The next method that we use will be to select the survivors, right? So over here, you can see that we want to introduce some randomness into the method, so we can actually apply the randomness to actually allow us to do a wide variety of tries. So you can see that over here, this is the table reflecting how survivors will be selected. Essentially, what this table highlights is the probability that this solution should be deleted, right? So all the solutions are being ranked, right? For example, over here, we are keeping a population of 25. So we rank the solution from 0th order to the 25th order. And this I actually represent the order, starting from 0 all the way until n-1, in this case 24. The probability of deletion depends on the order, right? If you're order number 1, which basically means that you are the best solution, your I value will be 0, which means that the probability that you are going to be deleted will be 0. And for the rest is going to be this I value divided by n, right? So even the worst performing solution, which is the 25th solution, the I value will be 24. So 24 divided by 25 is not actually 100%. So even the worst possible solution, you still have chance of survival. It's just that your chance of surviving is much, much lower than the better performing ones, right? Again, over here, the reason why we don't want to delete a solution for sure just because it performed very poorly is because we want to mimic the evolution process, right? Because one solution also in its current form may perform very bad, it still had the potential to contain some nice properties that later, if we are able to capture it, can be used to improve the current population, right? So that's basically the intuition. So the TSP lab can actually help you to visualize the current population as well, right? So if you type the command view map, what it does is that it will generate based on the randomly generated coordinate the current position of all the nodes. And on the right hand side, you will see a whole bunch of bars. Those bars is a representation of individual solutions. The higher the bar, the worse the solution, right? So it's actually ranked from left hand side to right hand side. Left hand side is the best performing tool because the bar length is the shortest. The right hand side is the worst performing solution. You have the highest bar. So if you call the select survivor method, what it does is that it's going to delete some of the solutions randomly based on the quality of the solution, right? If the solution quality is low, as mentioned, again, even the worst performing one, you don't have 100% of chance of deleting that, but the chance of it being deleted will be the highest. Okay, so you see that all these bars being grayed out, it basically means that the solution is now deleted. Okay, of course, you don't just shrink the size of the population, you will need to grow the population back. And this is achieved by a function called rebuild population. So you essentially will randomly pick a survivor, and then for that particular survivor, you will apply a point mutation. After that, that particular mutated copy of the existing solution will be inserted back into the population. Okay, so now you can see that the solutions that's been deleted from the previous page, which are 4 different solutions, they are being replenished, right? And you can see that some of the replacement can be worse, but some of the solution will become better. Okay, so if you combine all this together, this is what we call the evolutionary search. This e-search method, very easy to use. All you need to do is to specify a particular map object you like to search solution for. And the second number over here represent the numbers of iteration you want the method to run. And the final parameter is the size of the population. Okay, so very easy to run. You just specify the 3 parameters, and the method will run. So let's see one example over here. Okay, so this is, you can actually just start like anything. Again, remember, you have to specify, or you have to import the TSP lab first. Okay, so after you import that, you can create a map object by using the map constructor. You can create a map. So we create a size of, let's say, 25 cities. And then you can view the map. This is how you can visualize. Okay, so this is the visualization. We put it on the right hand side. So of course now you don't really see anything happening at the moment yet. So what you can do is that you can use the parameter that we mentioned in slides to execute the evolutionary search, right? 500 iterations with the population size of 10. So let's see how that will perform. Right, so you can see that the solution gradually improves, which is reflected on the left hand side as the tool. right? And again, you can see that the solution is flickering because some solution during every iteration was deleted and then replenished by the mutation of the existing solution. Okay, so you can see that this statistics show you the numbers of generations that we have gone through and the total numbers of tools that we have generated and the current cost of the best possible solutions that we actually have. Okay, so you can see that this particular method improves indeed from the original solution, but not by too much, right? So that's basically the issue. All right, so what can we do then to further improve the solution, right? So one thing, of course, you can try is to increase the population size. The previous number that we have is only 10, but if you have a larger map, for example, for the map of 25 cities, which is the one that we have just created, you might need more variation, more individuals in the population for the purpose of generating more promising solutions, right? For example, you can try a population size of 50 or 100 that allow you to actually increase the numbers of the solution that you can simultaneously monitor and hold. So one of the issues which we already see in the finding solution of the larger map is that no matter what we do, so even for the case where you have 25 cities, which by using local search you can solve it very easily, the population size can increase, but the help of it is limited, right? You see that even with a large population size, when the solution terminates, even like for example in this case with 10,000 iteration, which is a very long time, you still end up with this twisted version of the solution. You can try it out on your own computer. You will see that in most cases this is what will happen, right? Which basically tell us that maybe mutation alone is insufficient. We need other evolutionary mechanism to be introduced, right? Which is exactly what we will do next. So this is actually one of the most powerful mechanism in the world of biology that actually really introduce this genetic variations into the population. This is what we mean, what we call the crossover. So this is when a pair of parents come together, they contribute genetic material for their offspring. But again, the way the offspring's genetic material are being generated, are being decided, is to like take, roughly speaking, random half of the one of the parents' genetic material and combine that with another parent's genetic material. In the case of human, of course, we know that we don't just randomly cut the genetic material into two halves and combine the material from two parents. We always allow, like for example, one parent to provide one half, the other parent provides another half. So it's always 50-50, right? But in the for the purpose of generating solution, it doesn't need to be 50-50. We can randomly decide a point at which one solution will contribute, and then the rest of the material then will be contributed by the second solution, which play the role of the second parent. So in the context of TSP, the crossover basically means that we cut the path into two parts, and then for the first half, we take the route from the first solution, and for the second half, we take the route from the second solution. So a visual representation of how it works is something like this, right? So you can see that, for example, this box over here, the first gray box, this is the solution, the first solution, and the lower box over here is the second solution. You can see that both solutions individually evaluated may not be very effective because there are some good part of it and then there are some really bad part of it. But if you're able to cross over, let's say you are lucky enough, right, the point that you choose to cut it is actually the good point, the good part from solution 1 and the good part from solution 2. Then by making this one evolution move, which just basically span 1 generations, you can go from 2 very bad solutions to 1 almost optimal solution. And you achieve that by cutting this solution in half, or not necessarily half, right? Cutting this solution in the random place, right? So you decide that, for example, over here, you cut it over here, the upper part will be provided by solution 1, lower part will be provided by solution 2, right? And of course, there's always a chance that the combined solution will be very bad, right? For example, imagine if you take the lower part of the solution 1 and the upper part of the solution 2, you combine it together, it will generate a far more inferior solution than this 2 solution alone can achieve. But again, don't worry, because one of the very important force in the evolutionary search is, again, the evaluation of the fitness. If the solution is deemed to be unfit, right, you always have this survivor selection process that will allow you to eliminate the solution that's not competitive. Okay, so now we have this new mechanism. We can combine all of them and see how it works in practice. Okay, so the additional, we still use e-search, but the additional parameter that we'll be using is this distribution parameter. We set the distribution to be mixed, means that we're going to use both the mutation and also the crossover. So let's see how it goes, right? So this is the same map. We can actually just reuse exactly the same map, but we can execute the evolutionary search, right? We need a slightly larger population, right? Because over here you see that, I mean, if you only have a population 10, then you don't have enough variability. Okay, so you can make it, for example, still 500 generations, but you increase, for example, population size to be 50, but you allow yourself to specify a mixed distribution of the mutation and crossover. So let's see how it goes. Right, so you can see that, of course, it's improving because of larger population, but now you can also observe that you are making some more drastic change, and this more drastic change is made possible because you have the crossover. So some of the changes that's not possible based on the only the mutation now are being made possible because of the existence of crossovers. Okay, so you can see that now the paths look pretty much smooth out, right? And this is basically the kind of result you will never be able to achieve if you only base on your evolutionary search on the power of mutation. Okay, so this is basically it, right? So you can see that the principle of genetic algorithm, or some people prefer to call it evolutionary search algorithm, is actually very simple. You combine first of all the random mutation and crossover as a way that you can generate solution, and you apply this survival of the fittest principle as a way for you to continuously just eliminate unpromising solutions from population and replenish the population using the 2 methods that we talk about, which is mutation and crossover. So these few elements, when combined together, can generate actually very powerful outcome, right? You can give it a try. Ready available in the Python lab, and I will encourage you just to try it out, and then you can look at the source code, right? So if the methods you think that is promising, you can even try it out, give it a try in your upcoming project too, which again is the difficult problem if you want to solve it exactly. But all this heuristic that we have talked about, you can actually just try it out, and I think the good thing is that you have all the source code that's out there, right? So if you wish, you don't need to start from scratch. You can borrow the source code and just amend it so that it will work for the problem statement that's given to you. Okay, so the final point over here is on quantifying the efficiency, right? So evolutionary search have a couple of coefficient or parameters So this is making it different from the method that we have earlier, like greedy approach or local search approach. So we have to accommodate those additional parameters. So the major two parameters that we have is the population size and the numbers of generations. So we use P to represent the population size. We use G to represent the numbers of generations. So if population size is P, for example, if population size is 100, based on the probability table over there, right? If you calculate the expected numbers of survivals, you'll be roughly speaking 1/2 of the population, right? Because the way that the population elimination works, right? So you have this I from 0 to n-1, and the probability that that individual will be eliminated depends on the order, which is I divided by n, right? So if you write it out, it'll be something like this. You are essentially summing up I over n, right? So in other words, it's 0 over n plus 1 over n, right? Until n-1 over n, right? So if you calculate this, you will get 2n, and then n times n-1. Just cancel out. So the expected numbers of survival will be, roughly speaking, n-1 divided by 2, right? So you can actually put, the exact number is actually population minus 1 divided by 2, but we approximate that with the population divided by 2. And then again, every generation you generate P over 2 new tool objects. So total numbers of tool objects that you generate will be generation times P over 2 plus P. Okay, so if you multiply everything together, if you want to quantify your complexity as a result, right? G and P are all both given, so you cannot really remove them. So the complexity will be G times P, right? Dropping the lesser term, dropping the coefficient. All right, so you can also calculate the expected numbers of new tools that you generate. For example, we can insert this parameter over here, right? P equals 100, G equals 500. It gives you around 25,000 tool objects. So if you want to objectively compare the performance of different search method, right? For example, you can go back to this method over here. You can look at, for example, both numbers of tools and also the solution quality. E-search is the evolutionary search, and one alternative method you can also compare to is R-search, which stands for the random search, right? It's very simple, just the map object and numbers of iteration you want it to run, right? So for example, you can let it run for, let's say, 1,000 iterations, right? So you will just simply generate up to the numbers of tool object that you have specified. So for example, you can, if you want to make the fair comparison, you can go back and say that, for example, population is 100, generations 500, you actually look at 25,000 tool objects. So if you want to see how well the GA is compared against the random search, you can actually let the random search to search for 25,000 objects. Okay, so it will take a while and you will get the best possible solution that you will see if you simply randomly generate solutions. And the results will not be too good, right? So you can see that no improvement has been made after you generate this still pretty bad solution, right? And that will be how you can quantify the difference between a more directed random search, which is evolutionary search. You can see the solution quality you get is 1700 roughly. But if you only use the force of randomness, right, not much improvement has been made. It's only still the solution quality is close to 3,400, right? So roughly speaking, it's almost 100% of 2 times what the GA is able to achieve. Okay, so this is on the efficiency side that will help you go back and actually compare against other method. The random search you can compare to. You can also, for example, compare GA against the tool-up, which we actually have the source code for that. And also you can compare it against the greedy approach of both, like greedy 1, greedy 2. You can see which one is actually better. All right, so the final summary, this is summary actually not just for this week, but also for last week. Right, so for this 2 weeks, we have introduced TSP as one almost like the model questions to illustrate what to do when the problem we are facing is too complicated to be solved exactly. And TSP is ideal because you see that even with very small problem size, it's surprisingly complicated if you want to solve it by very naive method of going through each and every possibility. And random search also in this context, because of the size of possibility, doesn't work very well. So we have 3 important heuristic that you can actually try out given any kind of problem. Greedy approach is to decompose a long combinatorial consideration into 1 step at a time consideration. And because of that, you break the factorial complexity into the n squared time complexity, right? Because every step you only need to look at most n different objects, right? And then depends on the numbers of the step you have to go to. In the greedy case, you have to go through exactly n different cities, so it's n times n. You have n squared complexity. Local search will also show that is n squared times numbers of iteration you plan to run it. Right, so if you treat the numbers of iteration as constant, then it will drop off. But even you keep it as the parameter, the complexity is actually not too bad. Right, so these 2 methods should be very efficient, and they are complementary actually, because greedy approach always give you the same solution and is constructive approach. But local search algorithm need to have a starting location, a starting solution that you can work from. And you can imagine one way you can get the best of both worlds is that you use the greedy approach to generate 1 initial point, and then you use the local search to continuously try to improve it until you cannot improve it any further. Or, I mean, if you want, you can also, to increase the diversity of the local search algorithm, you can also, for example, randomly generate initial point, and then you, for each and every randomly generated point, you can try to improve it. This is one computational way of really increasing the diversity of your local search, because you know that the starting point actually have a very great impact on the eventual quality that you can actually end up with in the local search. The final method is the genetic algorithm. Right? This is the method that's inspired by the natural selection. Right? Again, very easy concept, purely computational, but I think the designing of the mutation operation or the crossover operation, you have to give it a thought, right? To think about how to best change those 2 functions in accordance to the context of your problem. Okay, so this is it for the TSP. We will end here.